Today we're going to be drawing the 5 isomers for C6H14. All right, so the first isomer is always a freebie. It's always the straight chain. This is what the straight chains look like in 3D. In 2D, you're kind of looking at them like this, and then they are obviously more in a line. So to draw this one out, it's just going to look like this. And they are going to be C6H14. And this is actually going to be true for all of them. Okay, now again, I went into this in more detail. No matter how you draw this, if you were to draw it like move it like this and move it like this and kind of make something like this even, that's still a straight chain as far as we're concerned, because the way that they're connected, they're still connected in order, meaning 1, 2, 3, 4, 5, 6. It's still a chain. Okay, it doesn't matter how the chain bends or snakes or does whatever it does, that still counts as the same straight chain. All right, now the way you make something different or an isomer is by disconnecting one from the end and then moving it in, typically 1 carbon in. And so now this, if I'll unfold it, make it a little bit easier, this is something different. This is 1, 2, 3, 4, 5 in a row, and then there is a methyl group on the second carbon in from the branch. So this is an isomer. Now, the way we draw it is gonna look like this. So there's 5 in a row, and then it doesn't matter if I go up or down, there's my branch. Now, common mistakes that I get with this is, again, this branch is the same as if I drew it like this. That's the same as that, just rotated. Which is the same as that. Which is the same as that. They're all the same. All I would do for the naming is I would number this carbon 1, carbon 2, and that would be 2-methyl. Call this carbon 1, carbon 2, 2-methyl. Call this carbon 1, carbon 2, that's 2-methyl. This is carbon 1, that's carbon 2. Okay, so these are all the same. These are all 2-methyl, and then since they're 5 in a row, pentane. So no matter what you do, it's the same thing. And then again, if we go back to the model, it does not matter if I twist this thing up like this and say, oh, well, there's like a ring here and this thing. Nope, it's still 1, 2, 3, 4, 5 in a row. And on carbon 2, there's a branch of 1. So that's how this works. So you can't use that anymore. But here's the interesting part about a larger hydrocarbon, right? We can get away with this. That is different, okay? And here's the reason why, if you haven't already figured it out. Whether you number it from the right or the left, it doesn't matter. Now the methyl group is on carbon 3. That would be the equivalent of me taking this methyl and moving it here. So now I've got 5 in a row with a methyl on carbon 3, the middle carbon. So the problem is, if you put it on the first carbon, on the carbon 2, well, if you put it on the first carbon, it's actually part of the straight chain, so it doesn't count as an isomer at all. If you put it on carbon 2, it's fine, but remember, if you draw it up, you could draw it down, you could flip it this way, you could flip it this way. It's all the same thing, nothing's changed. But if I disconnect it and move it to carbon 3, now it is uniquely different, because no matter how I rotate this, the methyl group will always be in the middle. So that does count as an isomer. All right, so be aware of that. That one is a very tricky scenario for that guy. What you're going to find is that the reason we didn't do this in the 5 carbon, C5H12, was because 5 carbons is just too short and there is no extra variant. The larger the chain gets, the more often you can get away with just moving the methyl group down the chain and finding different versions. So now to get another version, what we have to do is we have to also disconnect another one from the main chain and reconnect it someplace else. Now, here definitely counts. This is 4 in a row, right? We have 1, 2, 3, 4, and then a methyl on 2 and a methyl on 3. It doesn't matter if I call this 2, 3 or if I call this 2, 3. It doesn't make a difference which way I number it. So this is doing it again. So now I go to 4 in a row, and now I have a methyl here and a methyl here. Now, again, it does not matter if I draw them both down, both up, down, down, up. Doesn't make any bit of difference, because in real life they rotate around. They're free to rotate around that carbon that they're connected to. They're not free to disconnect and reconnect someplace else, but they are free to rotate in space. All right, and so there's your next one, because it's 1, 2, 3, 4. It's 2 methyl groups instead of just 1 methyl group. And then here's the final one, and this is the trick. Since I have 2 methyl groups, I can start playing around with where I move them, meaning this is different, because this would be 2 and 2, and then this is 2 and 3. Now, common question you get a lot is, well, what about this one? What about 3, 3? Well, 3, 3 is just 2, 2 flipped. Okay, it's the same molecule. So, for example, this would be, if I reconnect them, this is the last one. As you can see, I've got my 4 in a row, and then I've got my 2 methyls here and here. And if I move them over to look like this guy, well, all I'm doing is this. So it's the same molecule. I haven't reconnected anything. So these are all the variations of hexane. So that one's a little bit more. The more carbons you have, the more variation you have. All right, and so let's draw all our H's in. So there's all my H's. Again, to double check this and make sure these are done right, you're going to want to make sure every carbon has 4 bonds, and then count the number of H's that you have, and make sure you have 6 carbons and 14 H's every single time, and make sure all the carbons have 4 bonds. And once you've done that, you have done them all right. So now for the condensed, this should be pretty easy. So there's the first one, pretty simple straight chain. I'm always going to condense left to right. That's the way I like to do it. So even though I'm calling this, even though this has to be called carbon 1 because the methyl group is closer to this way or to this side, it wouldn't make a difference. If you drew it over here, you'd still call this carbon, you call this carbon 1, and it would still be 2 methyl in that case. But let's just, I'm just going to do it left to right to make it, just to be consistent. But depending on where you put your methyl, you could have put it down, up, or on this carbon, 2 in on here, down or up. It's all the same thing to me. It's going to be the same answer either way. Your condensed will be a little different, but that's fine. It's still correct. So there we go. There's our final, or our next one. For the next one, CH3, and then we're missing an H there. And then for the next one, and then for the last one, I'll just go straight to the fastest answer. Made a mistake. So since carbon 2 has no H's directly connected, we just write the C to represent that one. Then we do our CH3. And since there's 2 identical groups, just put a 2 outside to save time. So there's our condensed formulas. And then the last part is the names. So the names can be a little tricky, so let's go over them. This one is hexane. Now with this next one, I'll number them completely. The main chain only has 5 carbons in a row, so it's going to be, and then on carbon 2, there's a methyl group. So this is 2 methyl pentane. Since this one is moved, now this one is 3 methyl pentane. And for the last two, they are 4 in a row. So they're not even pentanes anymore, they're butanes. Okay, but since they have 2 methyl groups, they're going to need 2 numbers. So this one is called 2, 3 dash dimethyl butane, and this one would be 2, 2 dimethyl butane. We would never call this one 3, 3 because if we numbered from the other side, then it would be 2, 2 backwards, and so we always want the lowest possible number. And then this one, it doesn't matter which way I number because it's going to be 2, 3 either way, and it doesn't matter if you call this methyl 2 or this methyl 3. That doesn't matter because it's going to be the same. So that's everything for drawing slightly harder isomers. I don't think you'll ever have to draw anything, any isomer that's harder than this, but you could be asked to draw an isomer that has a double bond. And so also be aware, if you have a double or triple bond, the quick way to make isomers for those, obviously you can do all this reconnecting and adjusting the structure, but all you have to do is just move the double bond to a different location. If there is a true different location that isn't just some variation of the original location, and that counts as an isomer with double bonds. So those are the first couple isomers of anything with a double bond are pretty easy. You just get to move the double bond around. And then you run into, now you then have to do all of this while accounting for the location of the double bond. So as soon as you go to an alkene, you start getting way more variation and therefore way more potential isomers that you can draw. So that's why we're never going to do that. But I'm not saying that it's not outside of the realm of possibility. You could do it. It would just be, you'd have to pay a lot more attention to what's going on with every potential isomer probability. But that's it for this video.